110 meters below the surface. Crushing water pressure, freezing currents that never stop moving. And Istanbul decided to build a tunnel down there, one wide enough for 4 lanes of traffic and a metro line, running straight through the middle of it. Welcome back to the channel. Today we're re-looking at one of the most ambitious underwater tunnel projects ever attempted by human engineering, the Great Istanbul Tunnel. A $3.5 billion attempt to punch a third crossing beneath the Bosphorus Strait. This is not just a tunnel. It is an attempt to rewire the traffic pattern of a city of over 15 million people, stacked on 3 levels, buried under one of the busiest shipping lanes on the planet. This is not just a road connecting 2 shores. It is an attempt to weave together a road network, a rail network, and an airport system that were never originally designed to meet underneath the sea. And this is not just an engineering project. It is a political promise, first made in 2015, that has had to survive changes in government, shifting budgets, and more than one skeptical headline asking whether it would ever actually get finished. Let's talk about what stood in the way. A strait choked with international shipping traffic moving day and night that could never be paused for construction. A seabed sitting on an active seismic zone, capable of producing earthquakes strong enough to level buildings. Water pressure at depths most engineers never have to design for. A route that has to weave beneath an existing rail tunnel and an existing road tunnel without ever touching them. Property and land acquisition across some of the most valuable real estate in Istanbul. Currents that shift with the seasons. Silt and unstable sediment layers on the strait floor. The logistics of moving enormous prefabricated structures through open water without shutting down the strait to shipping. The need to tie the new tunnel into 3 separate airports and 9 existing metro lines without breaking the systems already running. A political timeline that has already stretched across more than one government, financing arrangements that had to be renegotiated as costs and timelines shifted. Environmental review processes protecting one of the most ecologically sensitive marine corridors in the region. Construction logistics for a workforce that had to operate both on the surface and far below it. Often on opposite schedules, public skepticism from a city that had already watched 2 other tunnel projects run years behind their original targets before finally opening, and a public that had already seen 2 other tunnels built beneath the same stretch of water and was going to compare this one against both of them. And they decided to build it anyway. Before we continue, make sure to subscribe to the channel because we cover the engineering stories most people never hear about. Stay with us until the end, because this is a tunnel that was announced over a decade ago, delayed more than once, and is still not finished. And the reasons why tell you almost everything about how modern megaprojects actually get built. To understand why this tunnel matters, you have to understand what it's trying to join. Istanbul is not a city that happens to sit near a strait. Istanbul is a city that is physically split by one. On one side, Europe, on the other, Asia. For most of human history, the only way across was by boat. Every army, every trader, every commuter who ever needed to move between the 2 halves of this city depended on a crossing of open water. The first fixed link beneath that water didn't arrive until the 21st century. The Marmaray rail tunnel opened on the 29th of October, 2013, the first time in history a train could travel underneath the Bosphorus itself. 3 years later, on the 20th of December 2016, a second link opened the Eurasia Tunnel, a double-deck road crossing running 5.4 kilometers in total. With 3.4 kilometers of that board directly beneath the strait, it was built by a consortium of Turkey's Salb Merkezi and South Korea, SSK Group. And it was engineered to withstand a magnitude 7.5 earthquake, a design requirement that tells you everything about the ground. 2 tunnels, 2 continents, and still, Istanbul's planners decided it was enough. The Great Istanbul Tunnel isn't meant to replace either of those crossings. It's meant to sit alongside them, deeper, wider, and carrying more at once than either one attempted on its own. Where the Eurasia Tunnel gave the city 1 deck of cars in each direction, the new tunnel is designed to carry 2 full road levels plus a metro line, all stacked inside a single structure at a depth of 110 meters below the surface. Look at the price tags side by side, and the scale of ambition becomes obvious. The Eurasia Tunnel cost approximately $1.2 to $1.3 billion to build. The Great Istanbul Tunnel is projected to cost roughly $3.5 billion, nearly 3 times as much, for a single structure attempting to do the work of 2. That's not a marginal upgrade. That's an entirely different category of project with an entirely different category of risk attached to it. And risk, in this part of the world, is never just financial. It's seismic, it's geological, it's political. Every single one of those risks had to be priced into a structure that, once sealed beneath the Bosphorus, cannot simply be reopened. At first, there was only water. No tunnel, no boring machine, no access shafts, just the Bosphorus itself, a strait that has separated Europe from Asia for as long as human beings have lived on either side of it. No structure beneath the waves, no fixed link at that particular point between Georete on the European side and Kuksu on the Asian side. Just open water, shipping lanes, and a seabed that had never been mapped for a project like this. No survey data, no confirmed route, no agreement yet on exactly how deep the tunnel would need to sit or exactly how it would avoid the 2 crossings already running beneath the same stretch of water. Just an announcement made in February of 2015 promising a structure that, at the time, existed only on paper. If you try to bridge a strait this busy, you run into a wall of shipping traffic that can never stop moving, and you build a structure that becomes a target for wind, for waves, and eventually for war. If you try to dig a shallow tunnel close to the surface, the pressure differential and the shifting sediment make it dangerous and unstable. Both approaches fail. The same basic tests: can it survive decades of use, an earthquake, and an active shipping lane? All at once, picture the strait itself for a moment. Tankers longer than several football fields moving through a channel that narrows in places to less than a kilometer wide. Ferries crossing constantly, weaving between the larger vessels. Currents that shift with the tide and the season, strong enough to challenge even experienced captains. None of that traffic was ever going to slow down for a construction project. And none of it could be allowed to. Whatever got built beneath that strait had to be built without ever touching the world moving above it. So the solution was not a simple crossing. It was a deep, pressure-rated, seismically engineered tube, sitting well below the seabed, built in 3 vertical layers, and connected to a road and rail network that didn't exist yet on either side. Here is how they got there: survey and research. Before anyone can dig a single meter under the Bosphorus, you need to know exactly what's down there. The strait floor is uniform. It shifts from rock to soft sediment, sometimes over the space of a few hundred meters. Engineers needed a precise map of every layer beneath the waterline before choosing a route. This is why, in the summer of 2017, a specialized geotechnical survey vessel began systematic soil surveys along the proposed Bosphorus crossing. Every meter of the seabed had to be tested, every layer had to be logged, every fault line nearby had to be measured against the tunnel's planned depth. The survey work covered a long list of various: soil composition, rock hardness, sediment stability, groundwater pressure, seismic fault proximity, shipping lane depth clearances, existing subsea infrastructure like cables and pipelines, the exact position of the Marmaray rail tunnel already running beneath the strait, the position of the Eurasia road tunnel a few kilometers south, tidal current patterns, seasonal water temperature shifts, marine ecosystem impact zones, histority Ushaman Dalp T. This was not a quick survey. This was years of underwater mapping, condensed into a route that had to satisfy engineers, regulators, shipping authorities, and a seismic risk model, all at the same time, and every one of those surveys had to happen without ever stopping the strait itself. The Bosphorus is not a quiet stretch of water waiting to be studied. It is one of the busiest shipping corridors on the planet, carrying oil tankers, cargo ships, and ferries every single hour of every single day. A survey vessel working here has to plan its movements around a constant stream of maritime traffic that cannot be paused, rerouted, or delayed for the sake of a construction project. Every pass across the strait had to be scheduled, cleared and coordinated with shipping authorities before a single sensor touched the water. The engineers already had a reference point for how difficult this kind of work could get. A few kilometers south, the team behind the Eurasia Tunnel had faced the same seabed, the same shipping lanes, and the same seismic uncertainty when they bored their own crossing. That project had proven a deep bored tunnel could survive this strait. But it had also shown just how unforgiving the ground beneath the Bosphorus can be, a lesson the new survey team could not afford to ignore. Then came the hardest part, choosing exactly where to dig ground and foundation preparation. Once the route was chosen, the real problem started. You cannot simply lower a tunnel into open water and hope the seabed holds it in place. The ground itself has to be prepared to receive a structure that will carry traffic for generations. Engineers had to stabilize the seabed along the route, reinforce weak sediment zones, and design a foundation system capable of resisting both the static weight of the tunnel. The chain of dependencies here is unforgiving. The tunnel needs a stable foundation. The foundation needs a mapped and reinforced seabed. The seabed needs continuous monitoring to make sure it doesn't shift once construction begins. Every foundation choice mattered. Get the depth wrong, and the tunnel sits too close to unstable sediment. Get the reinforcement wrong, and decades from now, a moderate earthquake could do catastrophic damage. Without a properly engineered foundation, disaster. With it, a structure that can survive one of the most seismically active regions on Earth. This step alone involved a long list of preparatory work. Seabed leveling along the entire proposed alignment, removal of loose sediment down to stable bearing material, ground improvement in acceptance in weaker sections, geotechnical instrumentation to monitor settlement in real time, temporary cofferdam structures near the shoreline access points, dredging equipment positioned to manage displaced material, silt curtains to limit environmental disturbance to the straits. None of this was visible from the surface. Ferries kept crossing, fishermen kept working, and 110 meters below them, an entire foundation was being engineered, meter by meter, in conditions almost nobody on either shore could see or imagine. Primary structure, this is where the project becomes genuinely audacious. The plan calls for a tunnel roughly 6.5 kilometers long beneath the strait, with an outer diameter of close to 19 meters, large enough to contain 3 full levels stacked inside a single tube. 2 of those levels are for road traffic. 1 is for a metro line. Imagine standing at one end of that tube before a single vehicle ever passes through it. A dark, circular void nearly 19 meters across, sitting 110 meters below the surface of one of the busiest waterways on the planet, built to eventually carry cars, trucks, and trains through the same physical structure at the same time, without any of the 3 systems interfering with each other. Building the primary structure required an enormous chain of engineering decisions, each one dependent on the lab pressure-rated tunnel lining sections, reinforced concrete segments, engineered for a seismic zone, waterproofing membranes, bat tasing, pressed pottered, and 10 meters. Structural centered capable of flexing slightly during ground movement without cracking. This was not simple concrete and steel. This was a layered, pressure-sealed, seismically isolated structure, built to function as 3 separate transportation systems sharing one shell. The chain of dependencies here runs deep. The road decks need a stable tube. The tube needs waterproofing rated for 110 meters of pressure. The waterproofing needs a lining that can flex without cracking during an earthquake. The lining needs a foundation that was surveyed, mapped, and reinforced years before a single segment was ever lowered into place. Every layer depends on the one beneath it. Skip a step, and the entire chain is compromised. And underneath all of it sits the same seismic reality that shaped the Eurasia Tunnel a few kilometers away, a structure engineered specifically to withstand a magnitude 7.5 earthquake. The Great Istanbul Tunnel inherits that same unforgiving standard, except now it has to meet it while also carrying a rail line through the same structure, at a greater depth with an even larger diameter to manage. Then came the connection problem. Secondary structures. A tunnel under a strait is only useful if people can actually reach it. The Great Istanbul Tunnel is meant to exist in isolation. It's designed to connect directly into the highways serving Istanbul's 3 airports and to link into a metro network made up of roughly 9 existing lines. That meant building an entire secondary layer of infrastructure on both continents before the tunnel itself could function as intended. Approach roads on the Asian side, interchange structures linking the tunnel to existing highways, ramps connecting the road levels to surface streets, station infrastructure linking the rail level to the broader metro system, ventilation towers to meter traffic, road users, pedestrian and safety infrastructures, road users, Pertation and Saferd Tappers Traptors, Pergetian Taferd Shab Birch Sepper Gibrie Genzes. The tunnel needs approach roads. The approach roads need land. The land needs to be acquired, negotiated, and cleared before a single access ramp can be built. This is precisely where the project has run into its most persistent obstacle, not the seabed, not the seismic risk, but the slow, difficult, often contentious process of acquiring land above ground. Every parcel of land mattered. A single unresolved property dispute on the surface can hold up a project that has already conquered 110 meters of open water below it. That's the strange irony sitting at the heart of a megaproject like this one. The hardest engineering in the world can be solved with enough time, money, and expertise. The hardest negotiations sometimes cannot. This is also where the tunnel has to prove it's more than a road and more than a train line. It's designed to tie directly into the highways connecting Istanbul's 3 airports and to link into a metro network built around roughly 9 existing lines. That means every interchange, every ramp, and every station connection has to be engineered to match systems that were designed years, sometimes decades, before this tunnel was ever announced. Interior and finishing. Assuming the shell of the tunnel gets built and the surface connections get resolved, the interior work is its own enormous undertaking. 3 separate transportation environments have to be finished inside a single 2-road surfacing and lane markings for 2 vehicle decks, barrier systems separating opposing traffic flows, rail track installation and electrification for the metro deck, signage systems for drivers moving between 2 continents underground, emergency lighting and backup power systems, air quality monitoring centrally, decenter disperfant, in tubes. Every system inside that tube had to be built to function independently of the ones above and below it, because a rail failure could never be allowed to become a road failure, and a road incident could never be allowed to interrupt rail service. Imagine being one of the engineers walking through this tunnel during the finishing stage, 3 separate worlds stacked on top of each other, inside a single tube, each one still under construction, each one needing to be sealed off from the others before any of them could be considered safe. Above you, the sound of road crews laying asphalt. Below you, the sound of rail crews setting track. Around you, the constant hum of ventilation fans testing airflow through a passage that will eventually carry tens of thousands of people a day. All of it happening 110 meters beneath a strait that never stops moving, above your head. The finishing work also had to account for something most road tunnels never have to consider: passengers on the rail deck moving at speed just meters away from vehicles idling in road traffic above them. Every wall, every floor, every ceiling inside that tube had a dual-purpose structural support on one side, acoustic and vibration isolation on the other, so that a train running underneath would never be felt as a rumble by the driver above it. Testing. Before any tunnel like this can open, every system has to be tested. Not once, but repeatedly, under conditions designed to simulate the worst-case scenarios. It might actually face structural load testing to confirm the tunnel can handle real traffic volumes. Seismic response testing, to verify the structure, performs as modeled underground movement. Water intrusion testing, along the full length of the tunnel, ventilation testing to confirm air quality standards, can be maintained with sustained traffic. Fire suppression system testing, emergency evacuation drills across all 3 internal levels, electrical and signaling tests for the rail deck, pressure testing on the tunnel lining itself, and full integration testing to confirm the road system, the rail system, and the ventilation and safety systems can all function simultaneously without interfering with one another. This was not a single inspection. This was a layered testing process, repeated until every system passed independently, and then repeated again to confirm they all worked together. The full list of what needed independent verification kept growing the closer the project got to complete its structural deflection, under maximum rated load response of the tunnel lining to simulated seismic events at multiple magnitudes. Long-term corrosion, resistance of every metal component, exposed to saltwater intrusion, backup power failover timing in the event of a grid failure, smoke extraction rates in a simulated fire scenario, evacuation timing for passengers on the rail deck versus drivers on the road decks. Above them, does every single one of these systems still work exactly as designed? Together, at the same time, under stress, every test mattered. A missed flaw in the ventilation system could mean poor air quality for drivers stuck in traffic 110 meters underwater. A missed flaw in the seismic isolation could mean the difference between a structure that flexes and survives. There was no room in this process for shortcuts, and no way to fix a mistake once the tunnel was sealed and operational. Final inspection. Only after all of that, the surveys, the seabed preparation, the primary structure, the secondary connections, the interior finishing, and the testing, does a project like this reach a final inspection stage, where regulators, engineers, and government authorities sign off before any vehicle or train is allowed through. And this is exactly where the Great Istanbul Tunnel story gets complicated. The project was officially announced back in February of 2015. Survey work began in 2017. Reporting from a few years ago described active construction, and a tunnel boring effort already underway, with a target opening year of around 2028. But more recent tracking on the project tells a different story, one where land acquisition issues have slowed things down, and the real start of full-scale construction may still be ahead rather than behind. This is not a project with a clean, finished timeline. It's a project caught between an ambitious announcement and a complicated reality. Compare that to the timeline of the tunnels that came before it. The Marmaray rail tunnel took years of planning and construction before its 2013 opening. The Eurasia road tunnel took more than 5 years of construction before it opened at the end of 2016. Both of those projects, difficult as they were, eventually reached a finish line the public could see, walk through, and drive across. The Great Istanbul Tunnel, more than a decade after its announcement, is still waiting to prove it can do the same at nearly 3 times the cost, and with a far more complicated structure to deliver. Most people who eventually drive or ride through this tunnel will only ever see the finished surface. They will see a smooth road deck, clean lighting, and a train gliding along beneath them. They will not see the years of underwater surveying that came before a single meter was dug. They will not see the seismic modeling that shaped every structural decision inside that tube. They will not see the land disputes on the surface that delayed the project for years before construction could even move forward in earnest. They will not see the layers of pressure-rated concrete standing between them and 110 meters of seawater. They will not see the engineers who had to design 3 independent transportation systems to survive inside a single structure in one of the most seismically active regions on Earth, without any of them being allowed to fail. They will not see the 2 crossings that came before this one, quietly proving that a tunnel under this strait could actually work, the Marmaray rail line in 2013 and the Eurasia road tunnel in 2016, each one a rehearsal for the far larger structure now being attempted beneath them. They will not see the years between the 2015 announcement and the survey vessel as first pass over the seabed in 2017. They will not see the gap between the optimistic construction times reported a few years ago and the far murkier picture that exists today, where nobody outside the project seems entirely certain how far along it actually is. They will not see the meetings between engineers and property owners on both sides of the strait, arguing over land that had never been touched by a project of this scale before. They will not see the models run and rerun to simulate an earthquake that has to happen yet, adjusting the design a little further each time. They will not see the quiet, unglamorous years where nothing appeared to move on the surface, while surveys, negotiations, and structural planning continued underneath the headlines. A finished tunnel erases all of that. It presents itself as inevitable, as if it always had to exist this way, smooth, quiet, functional. It rarely tells you about the version of itself that almost didn't happen, or the version that as of today still has to happen yet from above. The Bosphorus looks the same as it always has, ferries crossing, gulls circling, the 2 sides of Istanbul, separated by nothing more than a narrow stretch of blue water. But below, if this project reaches completion, there will be a corridor of concrete and steel sealed against the sea, carrying cars and trains between two continents, built specifically to survive an earthquake that has happened yet. This was not just a construction project. It was a bet that a city built across two continents could be stitched together a third time, deeper and more ambitious than the two attempts before it. This was not just an engineering challenge. It was a test of whether a government could outplan a fault line, a shipping lane, and its own bureaucracy. All at once, this was not just a tunnel. It was an attempt to answer a question Istanbul has been asking for over a century. How do you connect two continents without ever fully closing the gap between them? Every megaproject tells you two stories at the same time. Here is the story of what gets built: the concrete, the steel, the depth, the diameter, the price tag. And here is the story of everything that happens around the build: the delays, the disputes, the years that pass between an announcement and a ribbon cutting that may or may not ever come. The Great Istanbul Tunnel is, right now, still living inside that second story. It was announced with confidence in 2015. It was surveyed with precision starting in 2017. And more than a decade later, it still sits somewhere between promise and completion, caught in the gap between what engineering can achieve and what land acquisition, financing, and political timelines will actually allow. That gap is not a failure unique to Istanbul. It's the reality behind almost every tunnel, bridge, and rail line you've ever seen finished on a screen in a few minutes of footage. The parts that are hardest to film are usually the parts that take the longest: the negotiations, the surveys, the years of waiting for a single piece of land to change hands. The Marmaray tunnel took years to plan before it opened in 2013. The Eurasia tunnel took over 5 years of construction before it opened in 2016. And the Great Istanbul Tunnel, more ambitious than both combined, may still need years more before anyone drives through it at all. But if it does get finished, if the surveys, the seabed preparation, the primary structure, the secondary connections, the finishing work, and the testing all come together, the way they redesign to the result will be something genuinely rare. A single structure, 6.5 kilometers long, sitting 110 meters beneath one of the most historically significant waterways on Earth, carrying two continents worth of traffic, and a functioning metro line through the same shell. Two tunnels already sit beneath this strait, proving it can be done. A third is trying to prove it can be done bigger, deeper, and all at once. Whether or not this particular tunnel meets its 2028 target, the attempt itself says something about how far modern tunneling engineering has come and how much patience it still demands from everyone waiting on the other side. Every crossing ever built beneath the Bosphorus has told the same underlying story. In a different form each time a boat crossing became a rail tunnel. A rail tunnel became a road tunnel, and now a road tunnel is becoming something larger still, a single structure trying to carry roads, rail, and an entire city's ambition through the same 6.5 kilometers of seabed. Every version of that story took longer than expected. Every version cost more than the one before it. And every version, eventually, changed how this city moves. Somewhere between the promise made in 2015 and whatever finish line eventually arrives, the Great Istanbul Tunnel remains exactly what it has been since the very beginning. A bet on engineering placed against a fault line, a strait, and time itself. If you enjoyed this look at one of the most complicated infrastructure stories in modern Turkey, subscribe to the channel for more deep dives into the mega projects reshaping our world. Thank you for watching.